Welcome to this podcast on architectural acoustics. In this particular podcast, I will focus on the question, what is sound, and attempt an answer. All sound is produced by the motion of a source. This citation is from Marshall Long's books on architectural acoustics, which I will use as one of the primary references for these podcasts. And what this means is that the, for instance, clapping of two hands or two elements meeting, or an object simply creating a motion in space, will have the ability to create sound. This is what we see, for instance, in the image to the right, where we see the pressure, the wave propagation, the energy resolving from the clapping with two hands. But when we talk about architectural acoustics, we should notice that sound is a much broader study that refers to just architectural acoustics. In fact, we can see here the schematic or the drawing from Lindsay from '64, which features earth sciences, engineering, arts, and life sciences. And in that, we have architectural acoustics located as just one part of study of sound in relation to acoustics. Obviously, to understand, perform, and make architectural acoustics instrumental to the making in architecture, we are also interested in music, speech, potentially psychology as related to psychoacoustics, and so forth. So all these aspects are entangled through the study of sound. So what is sound? Well, sound is a compression of molecules in a medium, and we can see this, for instance, by using a tuning fork, which creates rarefaction and compression. So as the tuning fork swings to either side by motion, it will create rarefaction and compression, which means high and low pressure zones. So if you have pressure on the y-axis and we have time in the x-axis, we will see that there's a change in the pressure from going up and down in this waveform. As the waveform changes, or the molecules move, we have a difference in the pressure and velocities of the molecules. In this segment, or this, perhaps more clear, we have high velocity and low pressure, whereas the shorter segments here, the peak segments, we have high pressure and low velocity. And while we intuitively understand waves by moving up and down and up and down, a sound wave is a longitudinal pressure fluctuation that moves through an elastic medium. It is called longitudinal because the particle motion is in the same direction as the wave propagation. It's this direction. Which means, or the medium can be a gas, liquid or solid. Though in everyday experience, we most frequently hear sounds transmitted through the air. Again, a citation from Long. It can be somehow difficult to comprehend what a difference is between the transversal and the longitudinal wave. But when we look at the bottom illustration here, we see a movement up and down, which represents a transversal wave. The movement of the molecules are in this direction. In the case of a longitudinal wave, we see that the movement of the particles are in this direction. What we should also notice when we're looking at the red dots, which just represent one of all the molecules here, we see that the red dot, the molecule, does not move forward in space. It simply moves between two different pressure conditions, high and low. This means, of course, that the molecules do not move in space. It is the pressure that moves through space. These pressure differences can be described by the unit circle by circular motion. And this means that the sinusoidal waveforms are components of this circular motion, and therefore, through that, we can describe the amplitude and the time of this amplitude. So on the previous slide we saw that the wave started here in 0 and it completed its phase, its cycle as this. But the phase does not need to start in 0. The instant can also be at a different amplitude and create a different wave until it reaches its full circular motion to complete the waveform. A complete cycle is defined as the interval required for the waveform to return to its arbitrary initial value. And what we end effect here is the combination of phases of waves that form the composition of sound. Sound has different values, and it's the resultant of the medium that it travels through. So here we have the speed of sound, which results from the bulk modulus of the medium and the density of that medium. And the bulk modulus of the medium in Pascal is basically the substance resistance to uniform compression, where the density is the kilo per cubic meter. In the case where we have the physical conditions of air in 20 degrees Celsius, we have a speed of sound of 343.6 meters a second. Hence, the velocity of sound is directly related to the physical properties of a fluid. So when we look at this table here, we can again see what we just looked at. Air at 20 degrees Celsius has this speed, whereas air at 0 degrees Celsius has a lower speed. It has a higher density. A central description of the properties of sound is its frequency as related to the waves. The frequency is a number of times a cycle is reached within a given time period. So if we make the analogy as made here by Long with our beating hearts, stating that if our heart beats 72 times per minute, the period is the total time, 60 seconds in this case, divided by the number of beats, 72, which gives 0.83 seconds per beat. If we then invert the period to obtain the number of complete cycles of motion in that time interval, this is called the frequency. And in the case of acoustics, we typically have a period of 1 second. So to repeat, or trying to make this a bit more clear, is if we have in acoustics 1 second period and a 1 second period, but in this case we have 4 cycles within this period of 1 second, we have 4 Hz. Whereas if we have 14 cycles within this period of 1 second, we have 14 Hz. So when we look at musical instruments, we will see that they have very different frequencies that they can play within. Looking first to the grand piano, we can see that the frequency spans from 32 to 4K, whereas the bass has a much more limited range that it can play within. The harp here in the top also plays in a large domain of frequencies. While we normally say that sound spreads in an omnidirectional manner to all sides, the spreading of the sound is also related to frequency, as we see in this scheme here. So at the higher frequencies, we'll have a more targeted directional spreading or direction of the sound, whereas the lower frequencies, you have a more omnidirectional spreading. Another central aspect related to sound and what sound is, and particularly in relation to acoustics, is wavelength. The reason for this is that the way we measure or judge physical size of objects in relation to acoustics is directly related to the wavelength. For example, a sound will scatter or bounce over a flat surface that is several wavelengths long in a mirror-like manner. But if the object is much smaller than the wavelength, the sound will simply flow around it as if it were not there. This is called diffraction, and we'll talk about that in another podcast. This is something we can refer to or see if you observe the behavior of water waves as they pass by, for instance, an iceberg. Mathematically, the wavelength, lambda, is found by dividing the velocity of the air wave with the frequency, as we see here. Let's make an example of this. So we have the cello, as seen here to the right, playing in its highest frequencies around 700 Hz. You can go and look back in the scheme that was shown on an earlier slide. So what is the wavelength at this frequency? Simply, we derived the velocity of the wave with this frequency, and we will obtain a wavelength that is produced in the high frequency area of the cello at 0.49 meters. So here we see basically a scheme or an outline of wavelengths in response to frequency in meters and feet. So again, if we look at frequency around 700 Hz, it's about 0.49 meters. But we can also obtain the frequency based upon the length of a string that is played. So here we have a frequency description, mathematical description. Again, we have the length of the string, we have the velocity of the air wave, from which we can then obtain the frequency. So let's make an example again. The frequency of a string, therefore, is the velocity of the air wave divided by 2 times the length of this string will give us 228.66 Hz in this case. And then we follow the other equations that we had from before, where we find the wavelength by dividing the velocity of the air wave with the frequency, obtaining a wavelength of 1.5 meters. Remember, this is at this condition. So, in summary of this podcast on what is sound, sound waves are produced by pressure differences by a moving source. Sound waves are longitudinal waves. Sound is described by its wave speed, frequency, phase and amplitude. And the sound wavelength is a very central aspect to describe sound's relationship to objects, which is of course very, very important in relation to architectural acoustics. Thank you for watching this podcast.